Welcome back. In the last video, we defined what normal extensions are. In fact, we proved a theorem giving three equivalent conditions for an extension to be normal, and we also looked at another criteria for an extension to be Galois. So, it is a purely numerical statement which says that the degree of the extension should be equal to the order of the Galois group. Okay, so we have done quite a bit of material in the last few lectures. So, let us take stock and do a few exercises to make sure that we understand all the various features of what we have learned in the last few videos. So, today in this problem session, we are going to essentially look at several examples and show that determine what the Galois groups, determine if it is a Galois extension, if it is a normal extension and so on. So, in each of the below extensions, find the Galois group and determine if the extensions are Galois normal or normal. Okay, so we will do a few examples just so that we are familiar with this. So, some of these we have discussed before. Let us take this and Q. Okay. So, here the Galois group, I will quickly go over this because we discussed this already. Galois group here is trivial because cube root of 2 has only one possible image in K. In general, in complex numbers, cube root of 2 can go to cube root of 2, cube root of 2 omega, cube root of 2 times omega square. But the second and third ones are not in K. So, the only possibilities for image of cube root of 2 is just cube root of itself. So, this is a Galois group and the fixed field is K itself. So, this is not Galois because the fixed field is not Q, or equivalently the degree of the fixed field is 1, whereas the extension of the degree of the extension is 3. Okay. So, K colon K is 1, K colon K is, yeah. So, what I mean is K over Q has degree 3, but the Galois group has order 1. So, this is not Galois. It is also not normal, I claim, because for example, remember the second condition of the previous theorem. It says that if a polynomial, irreducible polynomial has one root, it splits completely. That is not the case here, right? X cube minus 2 is irreducible, has a root in K, but does not split completely. Because it only splits as a linear polynomial times a quadratic polynomial, because that other two roots are not in K. So, it is not Galois, not normal. And by the remark I ended the last video with, because this is characteristic 0, Galois and normal are in fact equivalent. So, if it is not Galois, it cannot be normal, but we have not proved that. So, let us separately check that in each example. The second example is also something that we have seen before. K is Q adjoint root 2 comma I and F is Q again. So, here the degree is 4 and the Galois group, again I will go over this fast because we have discussed this in detail in earlier videos. Root 2 can go to either root 2 or minus root 2, I can go to either I or minus I, and those 2 times 2 4 choices will give you a group which is isomorphic to this. Okay. So, maybe I have not quite proved this, that it is isomorphic to this. So, let us do that. So, there are 4 elements in Galois group of K over F, right. What are they? 1, sigma 1, sigma 2 and sigma 3. This is something that I have used earlier notation. So, I will not write them again, but sigma 1 sends I to minus I and root 2 to root 2. Maybe I am interchanging this, but it does not matter. Sigma 2 sends I to I, root 2 to minus root 2, and sigma 3 sends I to minus I, root 2 to minus root 2. So, here you see that sigma 1, sigma 2 is sigma 3. In fact, more directly, you see that sigma 1 square equals sigma 2 square equals sigma 3 square is identity. Each of them is an order 2 element. So, there are only 4 groups up to isomorphism, sorry, there are only 2 groups up to isomorphism of order 4. One is the cyclic group Z mod 4Z, which admits a degree 4 element. The other is Z mod 2Z cross Z mod 2Z, which is not cyclic. In other words, it does not have a degree 4, order 4 element. So, every element has order 2. So, this must be Z mod 2Z cross Z mod 2Z. So, that is the Galois group, and it is Galois because for example, the cardinality of the Galois group is 4, which is the degree of the extension, right. It is also normal because it is a splitting field of, so I am going to write this somewhat messily, but I hope this is okay. It is a splitting field of this because you take x square minus 2, it splits completely, you take x square plus 1, it splits completely. However, and further it is generated by the roots. So, it is normal and Galois. And the third example is more general example. So, let K be any extension of Q of degree 2. So, what we have is K over Q degree 2. So, I claim that here no matter what K is, I claim Galois is Z mod 2Z and K over Q is normal and Galois. So, this is true. In general, actually this is true even if you replace Q by any other field of characteristic 0. So, I will do this example here just to stick to a simple case, and we will discuss more generally what this means later. So, let alpha be in K which is not in Q. Okay. So, first observation is that K is Q alpha, right, because it is a degree 2 extension. So, if Q alpha is an intermediate field, it is either equal to K or equal to Q, because this product of these two numbers is 2. So, you can't have, you must have one of them equal to 1. So, either Q alpha is equal to Q, in which case alpha is in Q, but alpha is not in Q. So, Q alpha must be in K. Because K is a degree 2 extension of Q, it is not equal to Q. So, you can choose alpha. So, that I should have said first. So, there is an alpha in K, not in Q. So, K is equal to Q alpha. Now, let F be the irreducible polynomial of alpha over Q. Remember, it must be a degree 2 polynomial because it is a degree 2 extension. K is a degree 2 extension. So, alpha has degree 2. So, this is the irreducible polynomial. So, suppose alpha and beta are roots of F a priori in C or in some large field. Okay. So, we know then alpha plus beta is equal to B, right. This implies beta is minus B, so alpha plus beta is minus B, I think, because that is the negative. So, minus B minus alpha. So, this I claim is in K because B is in C, remember B, C are in Q, sorry I should say Q, alpha is in Q, K. So, B, C are in K, alpha is in K, so this is in K. That means K must be the splitting field of F over Q. So, this implies K is normal over F. So, that much is clear, right, because it is a splitting field. So, it is normal. So, why is a Galois group Z mod 2Z? Because here the point is alpha and beta, so you have alpha and beta are distinct. Okay. That is because this is because F is irreducible. Okay. So, F is irreducible. So, if alpha and beta are, and F is equal to x minus alpha times x minus beta. Okay. So, also so x is irreducible. So, you have x minus alpha times x minus beta is F, and this is here, if alpha is equal to beta, that means that okay, so one has to think about this a little bit, but if you have it is characteristic 0 is important here. So, let me just so here an irreducible polynomial cannot have repeated roots. Okay. So, this is something that maybe you have looked in ring theory courses in the past, and we will anyway come back to this when we talk about separable polynomials. So, the point here is an irreducible polynomial in Qx has distinct roots in any extension field. Wherever it has roots, the roots must be distinct. So, that means so if it is not irreducible, of course, it need not be, because you can have x minus 1 whole square. It has repeated roots, but it will not happen for irreducible polynomials. So, this is a fact which I will omit. I mean, any explanation of this I will omit for now, but we will come back to this later. So, that means sigma, so consider sigma from k to k sending alpha to beta. So, sigma is a q automorphism of k, because it is a splitting field. So, any map like this is an automorphism, and sigma is different from identity, because beta and alpha are different. Alpha goes to alpha under identity. Okay. So, Galois group is in fact so the cardinality of the Galois group is 2, which is the degree of the extension. So, k over f is Galois. So, any degree 2 extension is Galois. So, remark exactly the same proof, there will be no difference, will work to show that if k over f is a degree 2 extension. Okay. So, any degree 2 extension of characteristic 0 fields is Galois. Okay. So, the same proof, the only place where degree characteristic 0 is used is here. So, provided it is characteristic 0, in fact, more generally you can say this even in characteristic p, and we will do that later, but for now let me just end this problem with this remark. So, any degree 2 extension is normal, which is nice, whereas you see that degree 3 extensions need not be Galois in general, even in characteristic 0. So, this is not Galois, right, degree 3 not Galois. So, next let us look at the following example. So, 4, let us look at, sorry, this is also something that we have repeatedly seen. So, this is omega is primitive third root of unity, and cube root of 2, let us say, is a cube root of 2, real cube root of 2, and this is degree 6. This is something that you can easily conclude by the tower. So, this is 3, because x cube minus 2 is irreducible by Eisenstein, and one can argue that this must be 2, because omega satisfies a degree 2 polynomial over q, and it cannot be, so it is at least at most 2, and it cannot be 1 because this is real field, right. So, this is 2. So, this is 6. So, now the question that we want to answer is what is the Galois group, whether it is Galois and whether it is normal. So, immediately we can conclude that we know in fact that k is the splitting field of x cube minus 2 over q. Okay. So, k over q is normal, that is all, right. It is a splitting field because it splits, x cube minus 2 splits completely over this, and it is generated by the roots. So, it is normal. Remember, roots of this polynomial are So, all of them are in K, and if you remove any of them, you don't get K, you get something smaller. So, K is the splitting field. Okay. So, now let me address the question of what is the Galois group and what is the Galois extension, whether it is the Galois extension. Okay. So, actually I forgot to make a remark here. So, remark here is this degree 2 extension, any degree 2 extension of fields is normal. See, up to normality we haven't invoked anything about characteristics 0 or not. So, any degree 2 extension of fields is normal, but need not be Galois. So, this will be give us an opportunity to construct an example of a normal but not Galois extension. So, by suitably taking a degree 2 extension which is not Galois. Okay. So, that was the remark about this. Let us continue now. So, I want to now understand what the Galois group is. So, now let me invoke our standard mantra about how to construct field homomorphisms. So, possible images of cube root of 2 are cube root of 2, cube root of 2 omega. So, there are 3 choices. Remember, all of them are in K. That is part of the fact that it is normal. Okay. So, and possible images of omega are omega and omega square, because those are the only roots of its irreducible polynomial, which is x square plus x plus 1. This is the irreducible polynomial of omega O cube. So, omega and omega square are the possibilities. Now, one more fact I will repeat now, which maybe I haven't emphasized enough, is it is well and good to say that images of an element are its conjugates. Only possible images of elements, algebraic elements, are its conjugates. So, you have to take its irreducible polynomial and look at the other roots of the irreducible polynomial. But more is true actually. You can construct a homomorphism by sending an element to its conjugate. So, not only is looking at conjugates limits your constraints, but every possibility of an element in its conjugate will give you a homomorphism. So, you can construct a homomorphism from K to K. So, in other words, what I am saying is that there exists a homomorphism from K to K for every choice of images of omega and cube root of 2. Okay, this is a stronger statement. I am saying that first step is to limit the possibilities of images for omega, which are only 2, and images of cube root of 2, which are 3. So, there are 3 choices for cube root of 2, at most 3, at most 2 choices for omega. But now I am saying an additional statement, which is a stronger statement. You take any choice, for example, you take omega to omega, cube root of 2 to cube root of 2 omega. You can construct a homomorphism that way. You can take omega to any of these 2 and cube root of 2 to any of these 3, and you can construct a homomorphism that way. This is a consequence of extension theorems that we did in an earlier video. Very briefly, the point is you can take cube root of 2 and any other image, any other possibility, any other conjugate. You can construct a map because these are both isomorphic to cube root of qx modulo x cube minus 2. This is where the conjugate is important, because they have the same irreducible polynomial. So, you can construct this and then extension theorem can be invoked to extend it. So, you can put in this place, can put any conjugate here. So, this later part is extension theorems. So, first step is to construct cube root of 2 to cube beta, where beta is any of these 3 elements, or more generally for any alpha you can take any beta conjugate, and then you extend by extension theorems. So, all this song and dance says that there are 6 choices. In fact, let me say automorphisms. right? Because omega can go to one of the two possibilities and there are independent possibilities. Cube root of 2 can go to one of the three and you can choose them independently. So, there are 3 times 2, 6 things, and there are only 6. Because you take any automorphism of k to k and look at where cube root of 2 goes, it goes to one of these 3, and you look at where omega goes, it goes to one of these 2. So, it must be one of the 6 that we have listed here. And remember, once you determine the image of cube root of 2 and omega, the entire automorphism is fixed because k is spanned by these 2 as polynomials with coefficients in Q. Okay. So, that says that there are 6 homomorphisms. That means the Galois group has order 6, which is also the degree of the extension. This implies k over q is Galois, right. So, this implies that k over q is Galois. Very good. So, this shows that this is a Galois extension. So, it is a normal extension by the general theorem to be proved later, that in characteristic 0 normal and Galois are same. Because it is normal, that we already know. We already know it is Galois, but we are trying to prove this directly. So, finally, what is a Galois group? So, often this is the last thing, because you can determine Galois extension or not before this. So, now let us use some group theory. There are only 2 groups of order 6. When I say a statement like this, I always mean up to isomorphism. What are they? They are Z mod 6Z, the cyclic group of order 6, and S3, the symmetric group of order 3. Okay. So, now which of them is this Galois group? I claim that it is this and not this. Okay. So, why is that? So, for this I am going to exhibit 2 particular elements of the Galois group and show that they do not commute, in which case it cannot be abelian. So, it cannot be that. So, sigma is this choice that I take, cube root of 2 goes to cube root of 2 omega and omega goes to omega, and tau, remember, to determine a automorphism of k, all you need to specify is the image of cube root of 2 and omega. So, sigma has this property, tau sends cube root of 2 to cube root of 2, it fixes cube root of 2 and it sends omega to omega square. So, now what is, so you can check later that this is order 3 element, this is order 2 element, because if you do sigma square it will not be identity. However, if you do sigma cubed it will get identity. Similarly, tau square is identity, tau is not identity. So, these are both exercises for you. Okay, so, I won't do that. What I will now want to show that is sigma tau is not equal to sigma tau sigma. What does sigma tau do to cube root of 2? Sigma tau sends cube root of 2, first see where tau sends cube root of 2 to. It sends cube root of 2 to cube root of 2. Then what does sigma do? Sigma sends it to cube root of 2 times omega. Now, what does tau do to omega? It sends it to omega square. Sigma sends omega to omega, so omega square goes to omega square. Whereas tau sigma goes to, first you apply sigma, so that means you go to 3 root cube root of 2 times omega, and now tau sends cube root of 2 to cube root of 2, but omega to omega square. So, that will go to omega square times cube root of 2. Already you see that they are distinct. Just to finish it, let us see where omega goes under sigma. Under sigma omega goes to omega, but under tau omega goes to omega square. So, omega is the same image, but these are not equal. So, sigma tau is not equal to tau sigma, and this implies Galois group of k over q is not abelian. So, it cannot be the abelian group of order 6. So, that means Galois group is Z mod 6Z. Okay. So, that completes the analysis of this particular extension. So, that is the 4th one. Let me do one more. Let us do q adjoint 4th root of 2 over q. So, this is k, this is f. So, this is a degree 4 extension. So, now immediately you can see that it is not normal. So, you can take f to be x power 4 minus 2. X power 4 minus 2 has a root, but not all roots. because what are the roots of this? These are 4th root of 2 plus minus and plus minus 4th root of 2 times I. These are the roots. So, not normal. What about Galois? So, it is also not Galois as we show, because Galois group of K over Q, let me sort of run through this quickly, I claim is isomorphic to Z mod 2Z. Because what are the possible images of 4th root of 2? So, a priori in the complex numbers, it can be 4th root of 2, minus 4th root of 2, 4th root of 2I or minus 4th root of 2. But in K, because we are only interested in maps from K to K which fix Q, are 4th root of 2 and minus 4th root of 2, right. So, there are 2 of them. So, that means there are only 2 homomorphisms. One is the identity which sends 4th root of 2 to 4th root of 2. The other is non-identity which sends 4th root of 2 to minus 4th root of 2. So, here there are 2 possibilities. So, there is only one group of order 2, namely the cyclic group of order 2. So, that means the field extension has degree 4, but this is strictly more than the degree of the order of the Galois group, which is 2. So, this implies K over F is not Galois. Okay. So, this is not Galois, and we have also discussed the Galois group, but just let us for fun determine what is the fixed field of the Galois group. See, we know that K colon K power Galois Q is equal to cardinality of Galois K over Q, which is 2. So, these are all things that I have recalled, I have done in the past. So, this is 2 because this is Z mod 2Z. So, this is going to be a degree 2 extension of here, and that will in turn be a degree 2 extension of Q, because this is degree 4. But what is this? If you think about this, what are fixed by both this and this? In fact, what is fixed by sigma is root 2. See, root 2, so root 2 is fixed by 1 and sigma. See, because root 2 must go to under sigma, root 2 is 4th root of 2 whole square. So, sigma of root 2 is sigma of 4th root of 2 whole square, which is minus 4th root of 2 whole square, which is root 2. So, that is the proof. Okay. So, sigma is fixed. So, that means Q root 2, so of course, root 2 belongs to this, that I should have said first. Q root 2 is contained in the fixed field, but Q root 2 is a degree 2 extension. So, that means Q root 2 is equal to K power Galois. So, I went over this fast, but I hope you understood the argument here. So, this shows that you have, this is the first example where the extension fails to be Galois, and the fixed field is in fact strictly intermediate between the 2 fields we started with. So, it is actually not one here, not one here. Okay. So, I have one more example that I want to do, but let me stop the video here. We have already spent a lot of time on this, and then in the next video I will do some more problems. Thank you.